Good evening and welcome. My name is Margaret Mershon. I'm the Science Deputy at the Carnegie Institution for Science. And I thank you all for coming and joining us this evening. If you were to drive through the state of Wyoming, you'd likely see quite a few drilling rigs. In 2014, oil and natural gas were produced in 22 of Wyoming's 23 counties. You might also see, if driving in Wyoming's Bighorn Basin, a ribbon of bright red rock running through the exposed hillside. Scientists often call this band of rock Big Red. Big Red is a marker of climate change that occurred 55 million years ago, when the Earth, already quite warm, became even warmer very quickly over a very short period of time, a few thousand years. The fossils and chemical signatures in Big Red and other outcrops that date to this time tell a tale of massive floods, droughts, acid rain, ocean acidification, and insect plagues. Amazingly, life survived, but evolution wrought dramatic and rapid change. Many scientists see this event, termed the Paleocene-Eocene thermal maximum, as an analog to the human-caused climate change we are experiencing and largely causing today. Notably, the thermal maximum was characterized by a massive injection of heat-trapping greenhouse gases into the atmosphere and oceans. This spike, the causes of which are largely unknown, was accompanied by an increase in worldwide temperature by as much as 9 degrees Celsius. It is possible that such a drastic temperature gain and corresponding environmental upheaval could happen again if we continue to burn fossil fuels in coming centuries. Though no one can say with certainty that the Paleo-Eocene thermal event is a mirror to the global change we see today, it is at least a cautionary tale. Scientists have been warning us of dire consequences of our dependence on fossil fuels for over 100 years. Collectively, we don't seem to be listening. Some of us demand absolute proof, something that scientists cannot provide. Others say global climate change is a hoax. Still others cite natural causes. Most of us seem to be lying low, waiting to see what happens. According to many scientists, including our guest tonight, Dr. Heidi Cullen, this wait-and-see attitude is foolhardy. The wait-and-see approach may seem rational, Dr. Cullen says, but it's incredibly risky. There's a time lag between what we do and what we see in climate and weather. By the time we're really seeing the full impact of global warming, it is too late to fix it. As Chief Climatologist and Vice President for External Communications for Climate Central, a nonprofit environmental organization based in Princeton, New Jersey, Dr. Cullen has heard her share of climate change naysayers. She has spent countless hours talking to and defending fellow scientists, such as those at Carnegie's Department of Global Ecology, who give us study after study, year after year, telling us the Earth is changing because of what we are burning. Tonight, Dr. Cullen will address this issue. She will explore the challenges faced by scientists, journalists, and politicians as they navigate a world where drill rigs keep drilling, even as the land on which they sit bows to the inevitability of change. Dr. Cullen received her BS in Engineering and Operations Research at Columbia University, where in the year 2000, she also earned her PhD in climatology, studying at Lamont Doherty Earth Observatory. For the following 2 years, she was a research scientist at the National Center for Atmospheric Research in Boulder, Colorado. She spent part of this time back at Columbia on a fellowship working for the university's International Research Institute for Climate and Society. In 2003, she joined the Weather Channel in Atlanta, Georgia, as their first expert on climate change topics. At the same time, she served as adjunct faculty at Georgia Tech. In 2006, she began a television program on the Weather Channel called The Climate Code, later expanded and renamed Forecast Earth, where she interviewed leading scientists and community activists. Forecast Earth was the first weekly TV series to focus on climate change and other topics. It ended in 2008, shortly after Dr. Cullen moved to Princeton to join Climate Central. In addition to her work at Climate Central, Dr. Cullen also lectures at nearby Princeton University on climate topics and was, for a year, a senior research fellow at University of Pennsylvania's Wharton School. In 2010, she authored a book called The Weather of the Future: Heat Waves, Extreme Storms, and Other Scenes from a Climate-Changed Planet. She's also a chief science advisor for the Showtime series, The Years of Living Dangerously. Dr. Cullen is a member of the American Geophysical Union, the Society of Environmental Journalists, and the American Meteorological Society, where she was recently elected to the AMS Council. She also serves as a member of the NOAA Science Advisory Board and the National Academy of Sciences Board on Atmospheric Science and Climate. Please give a warm welcome to Dr. Heidi Cullen.
So much. All right. Thank you so much, Margaret, for the introduction, and Ben for the invitation, and for everyone who came out on a rainy, not such a nice weather night. And you know, the weather will focus into this talk, so we can kind of deal with that a little bit. You know, it was so nice of you to mention the PETM. So I want to talk a little bit about longer climate cycles in my talk tonight, and you know, I think really it's so much about, you know, the title of the talk is Seeing Things, and I think, you know, what I'd like to do in the next 40 minutes or so, and I don't want to talk too long because I really hope we have a good chance to do some Q&A at the end, because this really is kind of a magical moment in climate science right now with the COP coming up in Paris and with the Clean Power Plan just being published. I mean, there's so much going on, and there's so much important work to do. But I want to just, you know, walk through, really just for me, why I love science so much, and so much of it is about the way science helps us see things, and it helps us see things in space and in time, and climate science is so much about looking out over these longer time scales. You know, and of course, the beauty of science is the fact that when we really truly understand something, we then can predict it, and so much of climate change rests on our ability to trust these long-term forecasts. So before we talk about the bigger picture stuff, I want to just tell you a little bit more about Climate Central, which is an organization that I helped start up in 2008. And I think our mission really is to help people see climate change, because it's such a difficult topic to wrap your arms around. And so much of what we do is to try to use the science and to use the data to develop tools that allow us to get closer to this very, very thorny issue. And you know, when we started up in 2008, if you remember back then, the economy was essentially collapsing around us, and science journalism was taking a really big hit at that moment. And so our initial focus was really to bring scientists and journalists together. And Andy Revkin once said that, you know, that the heart of journalism and storytelling is heat and light, and so our thinking was that if we brought, you know, scientists into the same workspace as journalists, we would have the scientists providing the light and the journalists providing the heat, and we would kind of, you know, really be able to help folks connect to this issue in a new way. So we started up with a journalism effort, and you know, I'll say that we're a nonprofit, non-advocacy group, and you know, thanks to the Schmidt Family Foundation, Eric and Wendy Schmidt, we were able to launch back in 2008, and now, gosh, 7 years later, we've managed to generate several other programs. I think for me, probably because I came from the Weather Channel, I really felt that it was incredibly important to bring climate science into the local news, and to really work with local TV meteorologists. And I'll say that we've worked with Bob Ryan, who was on air for a long time here in DC, and you know, we work now with, gosh, close to 300 local television meteorologists, and we give them weekly climate science content. And I think what we found is that so many TV meteorologists are getting questions about climate change, and they want, you know, they want that information so that they can answer questions, and especially when extreme events are happening. They get tons of questions when an extreme event breaks out. And then there's these two other programs that really, I think, also deal with how do we see climate change. I'm going to talk a little bit more about a Surging Seas initiative that my colleague Ben Strauss developed, which is, you know, coming from the Weather Channel with weather.com, where you just kind of type in your zip code and get a forecast. I think the goal was, you know, can we do that with climate change somehow? Can we localize it? Can we bring it closer to people? And the sea level rise tool that Ben built, I think, is pretty amazing in helping bring that issue closer. And then we're going to talk about extreme weather, like I said, and so I'll allude to that more as we move forward. But first, okay, imagine waking up to this outside your front door. This happened September 8th, 1900. It's the deadliest extreme weather event in U.S. history. Upwards of 8,000 people died when a hurricane hit Galveston, Texas. And I'll say that when I first started at the Weather Channel, I came from a climate science research background, and I was kind of thrust first, into this TV world, which was totally new to me, and then also into this world of operational meteorology. And I had this amazing chance to work with just incredible TV weathercasters who, I think felt so strongly about this mission of trying to keep people out of harm's way. And this was back when we didn't have the tools. We didn't have all of the things that we now have in our hands that we've built to be able to offer up the kinds of forecasts that we now deliver. And so, this is Superstorm Sandy. This is the GOES satellite. And this is now what we can see. We can actually see a hurricane developing. This takes you through probably about 2 weeks. You can see Sandy working its way up the seaboard of the East Coast, and then you'll see it make that radical turn to the left. And right now, about 90% of the data that we use in weather forecasts comes from satellites. And so we have come an incredibly long way since 1900. And I guess for me, I am just in total awe of a weather forecast. I mean, I can't believe that we've done this and we've built such incredible infrastructure. And when it came to Sandy, let's take a look at the track forecast. With Sandy, I think the track forecast really kind of exemplifies what science allows us to do. I mean, the forecasters at the Hurricane Center, they forecast landfall 4 days out. And really, what this entails was just incredible. I mean, right now, I guess, the 5-day track forecast for hurricanes is better than the 3-day track forecast from 10 years ago. And I think 10 years ago, if forecasters had seen a track like this, they would have thrown it out. They wouldn't have been able to trust it. But now, with 10 years of additional data coming online, better models, and really, I think one of the things that maybe we don't talk about as much is that when an extreme event like this is making its way into people's lives, I mean, there's an enormous amount of coordination that's going on. So, as Sandy was forming, the National Weather Service, NOAA, they launched 600 additional weather balloons because they wanted to basically improve as much as they possibly could the atmospheric models that were being used, because they really drive the track and intensity forecasts. And they launched those 600 additional balloons because there was a trough coming off the Pacific, and they wanted to be able to capture that to really get the best possible track forecast. They also repositioned the GOES 14 satellite and put it into rapid scan mode. They sent 10 Hurricane Hunter flights over 4 days. So I mean, as this hurricane is unfolding, there's hundreds of people who are basically efforting the collection of all of this data to make a forecast that looks like that. That said, we lost over 100 people in Sandy, and so the goal is to get even better at this. And I transition now from weather to climate a bit because, weather, how far are we looking out, right? We're looking out about a week. That's the memory of the atmosphere. But with climate, we're looking backwards, we're looking forwards, and it's a different beast. Mark Twain said, "Climate is what you expect, weather is what you get." And I don't know if Mike McCracken is here, but Mike has said, climate is nothing really. It's a statistical construct. It doesn't necessarily exist. And Stephen Colbert basically described it as thousands of little weathers averaged together. And so, really, what is climate? It's an incredibly fascinating question when you come right down to it. So let's talk a little bit about that. So Margaret talked about the PETM, 45 to 55 million years ago. How do we actually look at climate? We look at rock formations, we look at ice cores, we look at coral records, we look at tree rings. And the goal really is to look as far back in time as we possibly can, because there has been so much change on our planet. And when I left engineering school and decided to study oceanography and climate dynamics, it was, I think, partially because I was just in awe of that change that could take place, over 4.5 billion years. And as part of my PhD research, I got really interested in a period known as the Holocene. So the Holocene basically started around 10,000 years before present, and it's this very special period, right? Because for the longest time, our planet was not terribly habitable. It transitioned fairly radically between very, very cold periods, very warm periods. It wasn't the easiest place to live. And Wally Broker actually has a great book called How to Build a Habitable Planet. And the thing that happened that made the planet habitable, at least for us, was a climate period known as the Holocene. So, roughly 12,000 years ago, this is the GISP 2 ice core, and you can basically see that we were some pretty sharp transitions, but we were in a fairly cold period. So as we were coming out of the last ice age, we transitioned into this very stable period, right? There's a lot of variability here, and then about 10,000 years before present, the envelope of variability shrinks. And so from a science standpoint, this question was, what was it about the Holocene? Like what happened? And coincidentally, that's when we saw the emergence of complex human civilizations. And so it kind of begs the question, to what extent does a complex human civilization require a fairly small envelope of climate variability, right? And so, when folks would ask me all the time, look, the climate has always changed. Why should we be worried about, the fact that humans are warming up the climate? Well, because we're not really well suited to climates that are vastly different from the one that we're living in right now, right? So yeah, the climate has changed, but we weren't around, when it was tremendously cold or tremendously hot. So I think it's like for me, this focusing point for acknowledgement of the fact that our climate system does have tremendous variability, but we now are kind of part of this system that's pushing it into a place that we're not very well equipped to deal with. And that said, the Holocene also had its share of variability. And so as part of my thesis, I got to work with some archaeologists who were studying a site called Tel Elan in northeastern Syria. And the archaeologist that I worked with, a gentleman by the name of Harvey Weiss at Yale, kind of had this radical idea, because for the longest time, archaeologists attributed collapse when they saw a dig site and they saw signs of collapse, or just basically people leaving the site for in some cases hundreds of years. The translation for the reason why that site collapsed was generally political. It was warfare, maybe disease, and climate was never really a kind of a good explanation. People kind of thought that was, I don't know, just some kind of a weak explanation. And Harvey brought me along to Syria with him, and basically what we did was we looked at ocean sediment cores to reconstruct the aridity of Mesopotamia. So basically, the Mesopotamian floodplain, which is coming off here, is taking basically dust and transporting it into the Gulf of Oman. And so, really what we looked at was just creating this record of aridity for that region. And I'll never forget, I had my own doubts about why that site had collapsed. And this gentleman here is Sargon of Akkad. And the reason why the Akkadian civilization is of such interest to folks is that it was actually the world's first empire. So what Sargon actually did was take these ancient city-states of Ur and Uruk in the Mesopotamian floodplain, and he connected them with the breadbasket that was further to the north. And so all of the food production was done outside of these larger city-states. And so we spent our time in northeastern Syria at one of these grain production facilities, if you will. And when my results came back, what it showed was that there was a big spike in aridity. And I remember we got it C14 dated, and I'll never forget when the C14 date came back, and it was exactly when Harvey's site showed signs of collapse. And so, I show you this picture of the Holocene, and while it does look relatively stable, that said, there's still these long, in this case, not hundreds of years or thousands of years, which our previous climate record showed variability across, but say periods of tens of years where you would get these increases in drought or just changes in the variability of the system. And for those of you who've ever read Jared Diamond's really amazing book called Collapse, there's many other examples of fairly sophisticated societies just being unable to deal with the change that's thrown their way. You know, and I've got a picture here of Easter Island. This is the Viking settlement in Greenland, and this is the Anasazi. And you know, what we see is, to a certain extent in all of these cases, climate playing some kind of a role. And I think that's kind of the takeaway. It's not to say that climate was the driver, but oftentimes climate can be the straw that breaks the camel's back. So we go from looking back to looking forward, you know, and I showed you this image from 1900, and now I'm showing you this projection that goes out to 2100. And I think, especially when you're a climate scientist, you know, a century is nothing, you know, and I think one of the problems that we see with climate change is that projections that go out, you know, to 2100, no one can deal with them, really. They seem too far off. But, you know, that's why I love that picture. It's a terrible picture, but that picture from Galveston is so powerful because, you know, it wasn't that long ago. And when you see how much we've been able to do in that time frame, I mean, it just shows you that you know, the projections that we're showing here, and basically what I'm showing is from the fifth assessment report of the Intergovernmental Panel on Climate Change, kind of the two ends of the spectrum. You know, the 2.6, the RCP, the concentration projection that shows a strong investment in renewables versus a business as usual scenario. And you know, here we're talking about maybe 1.5 degrees Celsius, and here we're talking, you know, 4 to 5 degrees Celsius. So, you know, basically 3 degrees Fahrenheit warming, and then say 7 to 10 degrees Fahrenheit warming. And a colleague of mine at Scripps, Richard Somerville, will say that, you know, RCP 8.5, which, you know, that temperature projection is tied to emissions scenario, right? That basically this is kind of the way we're heading right now, right? So we're at this very important juncture, you know, right about here. And, you know, and the difference between this and, you know, what Richard says is that this pathway, this brings us to a radically different climate. I mean, 10 degrees warmer, that really is taking us to places that we have never personally experienced before. So that's like another thing to try to internalize. But really, I think one of the profound things about this sort of boring map that kind of makes all of our eyes glaze over, you know, I know that it's true. The thing about it is that it's really different from a weather forecast, right? Because a weather forecast, I always think of it as like pure defense, right? You see a track forecast for, you know, Katrina or Sandy or Patricia, and it's like, okay, what am I going to do, you know, over the course of these next couple of days, or you know, at best a week or so, and it's purely defensive. But this projection is completely in our hands, if you will. It's basically pathways that correspond with different choices, right? And I always tend to look at climate change as this, you know, whatever, 150 years ago, we made a choice to go with a predominantly fossil fuel-based infrastructure. And we've since then learned that fossil fuel-based infrastructure comes with significant risks. They're risks that are tied into kind of longer-term systems, and so they're hard to see on short timescales, but those risks exist. And so the question now is, okay, we recognize that a mid-course correction needs to be done, so this is our chance, right? Do we actually make that mid-course correction now? And you know, and Margaret mentioned something that I had said before, which is, you know, the tricky thing about climate change is that you actually have to believe that this is going to happen, because you can't make the change then. You have to make the change here, because the time lags in the system prevent us from fixing the problem when it's already staring us in the face. And that's a conundrum, right? That's a hard thing. So I showed you a time projection, so showing you something that we could see out in time. And I want to show you now kind of an impacts projection, because this doesn't really have a time frame attached to it. And this is essentially the tool that Ben Strauss and some of my colleagues at Climate Central built, which is based on all the tide gauge data. And it's an interactive tool that allows you to really drill down and see sea level rise risk. And a paper that Ben authored just last week attempts to really show this concept that we call the lock-in, right? And the thing about climate change, and the other projection that I showed you is the same thing, is that we're making commitments. We are actually locking ourselves into a future right now. And that's, again, the tricky thing about climate change, is that you're making commitments, you're making promises to things that you're actually not going to see for a really long time. And that's what makes this a thorny problem. So really, that RCP, that one scenario that I showed you previously, unchecked pollution, kind of a massive business as usual, if you will. This is the Washington, D.C. that we get. So this is really about 23 feet of sea level rise. And again, there's no time frame attached here. It's kind of like if I put an ice cube on the table, I can basically issue a forecast that says this ice cube will melt, but it's really hard to say exactly when that ice cube will be fully melted, right? It's the same thing with sea level rise. You know, we have projections that basically say maybe 3 to 4 feet by the end of this century, but again, we're making greenhouse gas commitments now that lock us into a certain pathway. And so if we do nothing, this is what we commit ourselves to, versus if we go with that, you know, renewable intensive pathway, this is what we lock ourselves into. So this is kind of a 1.5 degree commitment, and this is more of like a 7 degree commitment. And so again, you know, what it really shows us is what's at stake in these Paris discussions, right? And I think for me, having worked at the Weather Channel and being part of this team when extreme weather events happened, was to really see how vulnerable we are, right? I mean, I don't think we often, except in those really intense moments, realize how much is at stake and how much we have to lose, especially when it plays out over these longer timescales. So that's why I want to talk a little bit about how we actually process risk. And it's kind of an interesting business, and there's many social scientists who focus on this, and part of what we've been doing at Climate Central is trying to understand that social science literature. And really what it boils down to is, you know, this person sees this risk very close, right? This is a real urgent risk. And when it comes to climate change, this is the image actually that comes to most people's minds. It is melting ice. You know, it is this thing that is kind of cool looking, and it's distant in space and time, and that's really, I think, one of the hearts of the problem, which we've been talking about so far already, and that is there's a whole theory called construal level theory, which basically says that there's 4 different ways that something can be distant. It can be distant in space, it can be distant in time, it can be socially distant, so like none of my friends care about this, so I shouldn't. And then it can be hypothetically distant, which is, it is so unlikely, you know, that a meteorite is going to land on my head that I'm not even going to worry about it. And climate change kind of touches all of these types of distance. And I think for us, you know, this question is how do we take this issue and make it close? Because until it's close, it's going to be really hard for us to work on. And you know, there's a great book by Danny Kahneman called Thinking Fast and Slow, and if anyone's read it, it's all about these 2 different systems of processing information. One is sort of the fight or flight part of our brain, you know, the guy standing on his roof looking at the fire coming towards his house, where you're in full-on fight or flight mode. And then there's the prefrontal cortex, that part of our brain that actually processes risk using data. It's long-term thinking. It's actually the compassion component of our brain is there too. And so I often kind of feel like it's our prefrontal cortex that actually makes us human. But we actually use our reptilian brain, if you will, to process risk a lot of the time. And I think one of the challenges with climate change is that it's all over here. It's all processing large amounts of data, looking over long time scales, thinking about things that aren't staring you right in the face. So that's the challenge that we need to overcome. And this is sort of the classic way that System 1 and System 2 is broken down. One is personal experience, right? You know, I've personally been through this. I've seen it. Talk about seeing is believing, right? So seeing things is really important. And then, the whole logical component, right? So these are the two sort of different systems that engage when we process risk. And climate change doesn't really have a lot of that experiential part. But the experiential part actually comes in through weather. And so we'll talk about that more. So John Krosnick, a social scientist at Stanford, asked the question, how does an issue like climate change become urgent for someone? And what he found was that there's a couple of things that you needed to strongly believe in. One is the belief that it's caused by human activity. So if you don't think that climate change is caused by burning fossil fuels, you're really not going to think it's your problem, so to speak. There's also a big issue of having trust in what scientists say. And that's why, when I show this projection for 2100, unless you believe that scientists are actually telling you the truth when they're saying that that's a really, really, really bad thing and we need to stop it before it happens, you're not going to do anything. And then there's the consensus part. And I'm sure, as you guys know, there's been a lot of energy put into this thinking that there's a lot of disagreement on the science, when in fact there's not. And a lot of that energy has been put there because it's really effective. If people don't think that scientists agree, it's another reason to sort of just wait and see what happens, right? And then finally, it's the cues that we get from those around us, from the media, from politicians. If no one is talking about it, it can't be a big deal, right? So that's, I think, the other things that we need to keep in mind. This is a survey that comes out from George Mason and Yale, and really what it shows is that only about 40% of Americans hear about global warming in the media at least once a month. So in terms of the attention that it's getting paid, we're not really hearing about it very much. So not very much coverage. And as a result, most people still think global warming isn't going to harm them personally. So how do we talk about climate change? Really, there's 4 basic concepts, and it's 7:15. So do I have until about 7:30? 7:45. Till 7:45? Okay, good. The 4 key concepts I think are really important, and they're really important to keep them all together, because I think as scientists we tend to sort of separate them and talk about only what we know about, and I do think we have to have kind of the entire conversation. And I have to say, with Thanksgiving coming up, there was a survey that was just released that basically said, roughly 70% of Americans think that climate change is a problem, but roughly 60% of Americans don't want to talk about it. And I always think about this during Thanksgiving because it always comes up for some reason at my Thanksgiving dinner table. So if anything, this talk is just meant to prep you for Thanksgiving so that when it comes up, you're ready. So the 4 key concepts are pretty simple, right? It's real, it's us, it's a threat, and then crucially, we can fix it. Because if you stop at it's a threat, which is where a lot of folks in my world kind of tend to stop because we're not experts on the we can fix it part, that's kind of a different sector. If you don't talk about the fact that this is infinitely fixable, I'm not saying it's not easy, I'm not saying it's not hard, whatever the wording for that is. It's hard, it's definitely hard, but it's fixable, right? And it's really important to talk about that. So let's just kind of cover those bases. Here's the it's real. This is a NASA graphic, and it basically is just showing you the temperature anomalies moving through time. And to me, it's pretty amazing because, again, the things that we can see, right, the things that we're able to visualize because we have data, because there's lots of nerdy people out there like me who love to collect data. And basically what you're seeing is it's warming pretty powerfully as we move into the latter part of the 20th and 21st century, and this is where we're at now. And I think what it also really points out nicely is that global warming doesn't mean it's going to warm uniformly everywhere at the same time, right? There's still going to be pockets of cooling, and so when you get a cold winter in the Northeast like we did last year, I can tell you it really hurts the climate change conversation. Like it makes a big difference, and there's plenty of studies that show that. There's this thing called attribute substitution, right, where we have this tendency to take the weather, again, that we're personally experiencing and substitute it for climate change. So when it's warm, we think that global warming is real, and when it's cold, we kind of feel like it's not a big deal. So like our own bodies work against us, which is challenging. So it's us, and this story to me is always really powerful because this is one scientist who really decided that he wanted to start measuring carbon dioxide. That there was Svante Arrhenius back in the 1800s and Bert Bolin and just great scientists who essentially said, look, we're burning coal and that's emitting CO2. We should actually be able to measure that increase in the atmosphere. And so basically David Killing said, I want to do that, and he found a pristine location in the middle of the Pacific Ocean on Mauna Loa in Hawaii. He set up a monitor and he began recording carbon dioxide. And lo and behold, he was measuring this increase. So, all of the hypotheses that had been put forth that burning fossil fuels should leave a fingerprint in the atmosphere, Keeling showed was true. And the other thing that we don't talk about enough is that the other thing that Keeling did was that he chemically fingerprinted the CO2, right? So carbon dioxide comes in these different flavors. So there's C12, C13, and C14. And we know that C13 and C14, because they decay over time, are going to be lower in ratio. And so he could actually measure the chemical fingerprint of the CO2 in the atmosphere. And what he showed was that basically 1 out of every 4 CO2 molecules in the atmosphere today is put there by us, by human activity, which gets back to how we know that we are part of this, right? So, Keeling is a god. He's amazing. So it's a threat. Here's global temperature and CO2. They're strongly correlated. Here's decades of warming, right? The whole point is that each subsequent decade has been warmer than the last. I mean, they look really boring, but they're incredibly powerful statements, right? They don't really create a visceral reaction in us, but they're powerful. But here's, I think, where we can really begin to connect with people, and that is around this issue of extreme weather events. And really what this shows is, a probability distribution function, and this is the average temperature. And really what it's saying is, we hear this term, the new normal, and I think it's a really powerful term, but what it basically means is that the new normal means that this whole PDF has shifted, and it's shifted in the warmer direction, which more or less means that we should be seeing more heat extremes, right? So theory tells us that if you increase the average, you should see an increase in the extremes. So this holds for temperature as well as precipitation. Because of the Clausius-Clapeyron equation, if you heat up the atmosphere can hold more moisture, which means that we should also be seeing more intense precipitation events, right? So then what do? We go to our observational data, and we begin to look and see if this is holding true. And I think this is where this conversation around climate change and extreme weather can really begin. And here's a picture from the Australian heat wave in 2013, and if you remember, there was a lot of media coverage because the Australian Open was going on, and you literally had tennis players just like fainting on the court because I think at one point, David Crowley, one of the scientists that I work with, said that I think it was something like 123 degrees on the court. It was just insane. And so it sort of begins to ask this question: to what extent are we actually playing a role in these individual events? This is a picture from the UK flooding that happened in 2014, and this is a picture of the California drought. And I can say that each of these events, scientists have studied to look for a human fingerprint in these events. This is just a summary of the state of the science around extremes, and what it tells us is that when it comes to things like precipitation, heat and cold waves, floods and drought, we have a fair amount of confidence of how climate change, how the burning of fossil fuels can impact those events. And so I'm kind of moving us now in this direction of looking at individual extreme events and posing this question: how are we changing the weather that we're experiencing right now? So let's first look at observational data, right? So before we look at any individual event, let's actually just look at all the observations and see what they're telling us. So here's one way of looking at temperature. Temperature is pretty straightforward. Like I said, if you increase the average temperature of the planet, there's plenty of reasons to expect to see an increase in extremes. So some scientists at NCAR actually looked at that, and they basically broke it down. So this is the ratio between warm extremes and cold extremes. And in a purely naturally forced world, you would expect a roughly 1-to-1 ratio, which we had for a fair bit of time. Then we saw this progression, and now in the 2000s we were at, conservatively, for every 2 record highs we saw 1 record low. That has actually gone up. Now we're at 2015, and that ratio has increased. The other thing that Jerry Meal and colleagues at NCAR did was that they ran their climate models forward, and they asked the question, okay, if we're seeing 2 record highs for every 1 record low now, what happens by the time we get to 2050? On a business as usual scenario, we're basically seeing 20 record highs for every 1 record low. And by the end of the century, we're seeing 50 record highs for every record low. So kind of imagine what that would feel like. I said the same for precipitation, right? More moisture in the atmosphere suggests that we should be seeing an increase in heavy downpours. Well, we looked at that for the National Climate Assessment, and sure enough, across the entire US, we're seeing this shift towards heavier rainfall. It's more pronounced in the eastern part of the country. And so really what we're seeing is that increase in temperature is leading to heavier downpours, and so that fingerprint exists. So, a colleague of mine, Miles Allen at Oxford University, basically took the quote, "Climate is what you expect and weather is what you get," and he rewrote it. And he said, now, climate is what you affect and weather is what gets you. So let's just look at extremes and kind of ask this question, you know, what can we understand about the human influence on extreme events? And to give you a little overview, this is a science called extreme event attribution, and this dates back to a paper that Miles wrote in 2003, and it got straight to this question of liability. And I'll say that this is kind of playing out a bit in some of the Paris negotiations, and it's making things harder and more complicated, as if it wasn't hard and complicated enough. There's also now this question of, do developed nations have a responsibility for the extreme weather that they've potentially increased? And that is now definitely hurting developing countries, right? So Miles kind of posed this question, and relying on epidemiology, right? So sort of doing an autopsy on a human to assess, how, let's just say, cigarette smoking increased the likelihood of lung cancer. Miles kind of proposed this concept of fraction of attributable risk, looking at, okay, how did climate change or the burning of fossil fuels increase the likelihood of an individual extreme weather event? And so, I say here, it's not asking, did climate change cause the event? It's asking, to what extent did climate change increase the likelihood of that event happening? Just like with health risks. So, Miles kind of laid out this method, and then that same summer, actually, a massive heat wave hit Europe. Upwards of 35,000 people died. I remember I was at the Weather Channel at that time, and it was crazy, like to see what was unfolding in Europe in 2003. And we've seen it happen in multiple places since then. It's incredible. Based on our long-term records, it was probably the hottest summer since at least 1500 across a fairly large swath of Europe. And so basically Miles, Peter Stott, and Dahi Stone did the very first attribution analysis on that heat wave. And what they found was that climate change doubled or possibly quadrupled the likelihood of that event. And I don't know, I remember at the Weather Channel, for me, it was always really hard because this extreme event would happen and there would just be so much drama around the event, and obviously so much human tragedy. And then, they would kind of ask me to come in and say something, and I just never felt like I could say anything really helpful, like other than, yeah, we can expect to see more of this in a warmer world. But this paper, I felt, really kind of changed the conversation, because it looked at that specific event and said that, yeah, there was a human fingerprint in making that event more likely. And the thing that they did here was they also ran their models forward, and what they showed was that if we do nothing, by 2040, the European summer is basically happening every other year, and by 2070, the European summer of 2003 becomes the average summer. So that's kind of the way we can look at one individual event and then understand what that means in terms of the longer term trend. And so how do we do this? I use a baseball analogy. I can't decide if I'm a Mets fan or a Kansas City Royals fan. But given that we're in the World Series right now, I thought I would break out the baseball analogy. And really, it kind of is this question of is our atmosphere on steroids, if you will, right? And so this whole question about did steroids cause that home run? Well, again, this question kind of is talking to the climate system, right? And the way we do this in models around individual extreme events is to actually kind of create two realities. One is the world with us, with greenhouse gases in it, and then the other is what we call the counterfactual, which is the world without us. And basically you run those models and you look at how likely that event is. So you basically look for that 2003 heat wave in your two different worlds, and then you look at the difference. And what we saw was, in the 2003 heat wave, in the world with us, it happened twice as many times, right? And so moving forward, that's one of the ways that you can untangle this human influence. There's other ways to do it as well, but that's one of the key ways to do it. And I'll say that I've kind of been tracking extreme weather coverage for a while now, and I often will see, my own colleagues oftentimes repeat this phrase, and the phrase is, of course, you can't attribute an individual event to climate change. I will say that President Obama has said it, many other folks have said it, but the science has really moved forward. And this actually is from BAM's special report, and Chris Field, who's at the Carnegie Institute at Stanford, was an author of this paper. And what it showed back in 2012, it says it was often stated that it simply was not possible to make an attribution statement about an individual weather or climate event. However, scientific thinking on this issue has moved on. And now, at least in scientific circles, it's widely accepted that we can do this. And so, for me, I think it's really important that we move beyond this kind of knee-jerk statement of course you can't attribute any individual event to climate change, because that's another one of these things that kind of creates distance, because we actually can do it. And when you do it, like I said, the answer, I think, is pretty, it's a big deal. So one of the things that we've been doing at Climate Central is bringing together the scientific community to actually look at these events in a rapid manner, to do it as quickly as possible. And I'll say that there's four different outcomes. One is global warming increased the likelihood of the event. The other is global warming decreased the likelihood, right? So cold events, last winter aside, cold events are actually becoming less likely as the planet warms. The other is global warming had no detectable role. In our analyses, we couldn't find a strong influence of climate change. And then there's just this event is too crazy, too rare, too hard to really disentangle the players. And I'll say that right now, we have this very, very large El Nino playing out, and El Nino again is one of these things that has an enormous impact on our climate system. So a lot of the additional warming, 2015, as I'm sure you guys have heard, 2015 with 99.9% certainty is going to be the warmest year on record, in part because of El Nino, but also because of global warming. So those two things are kind of working together this year. So I'll say that our team got together, and we've been looking at different individual events, and over the summer we actually saw the weather forecasts coming out, and we saw that there was another heat wave heading for Europe. And so what we attempted to do was something very similar to the Peter Stott paper on the Europe 2003 heat, but we attempted to do it over a long weekend, if you will, because it actually happened over July 4th weekend. And so our team assembled, pulled together all of the data that we possibly could, and looked at this 3-day heat maximum. So we defined the event in terms of 3-day high temperatures, and what we found was that climate change made this event twice as likely over a large part of Europe, and then 4 times more likely in some of the hottest cities. And so what we're actually able to do now is not just look over a large spatial region, but to actually drill down. And we looked at individual cities, because there were cities that were just really experiencing some incredibly high temperatures. So we did this analysis for, Zurich was one of the cities that we did. And what we found was that This event is 8 times more likely than it was around 1900, and you can calculate the return time period, right? And so the return time is now roughly every 13 years, whereas back in 1900, it was a roughly 1 in a 100-year event. And so again, it's a way, I think, to make the event and our influence on the event feel closer. So I'm kind of begin to wrap it up now. How am I doing time-wise? Good. One of my favorite, it's kind of a downer quote, but it's a great quote from Sherry Rowland, who got a Nobel Prize in chemistry. He was one of the guys who found the ozone hole. And Sherry basically said, what's the use of having developed a science well enough to make predictions if in the end all we're willing to do is stand around and wait for them to come true? Well, we can't do that because we have to fix it, right? And so at the beginning, I just alluded to the fact that this really is an incredibly important moment in time. There's been a lot of important moments that we've always hoped would kind of tip us over the edge. This is another really huge opportunity. As you guys probably know, last week marked the publication of the Clean Power Plan, and this was our country's real sort of step into, I think, a demonstration of leadership on the international stage, right? I mean, our delegation is going over to Paris, and I think the U.S. really needs to show leadership on this issue, and this has been there's been many ways to do it, and this is one way that we're moving forward. And so the Clean Power Plan is focused on reducing carbon emissions from power plants 32% from 2005 levels by 2030. And it's meant to give states flexibility. It's kind of a cap and trade program in some respects, and states can kind of work together. And each state has kind of a different goal that they need to reach. The biggest polluters have the highest goals that they need to reach. In places like California, can actually, pollute more if they want to. It's one of these interesting things. There's actually an interactive on the Climate Central website if you want to check it out. And as you can imagine, it's controversial. It's a controversial plan, and at least 24 states are ready, and a host of coal and power industry opponents basically have already moved to file lawsuits. So it's going to be an interesting conversation that we see play out over the next couple of months. And November 30th is when COP21 starts. So COP1 was Berlin in 1995, and I think that really, if we think about the way these big international negotiations have worked, trying to get 190 countries to agree on anything, I mean, you can't imagine a harder problem, right? Climate change is really hard, and then you've got to get international agreements in place. It's daunting, but I give the folks who are working on this tremendous amount of credit for moving forward in the process. And really, if you think about Berlin COP1 1995, I think so much of it was about hard targets on emissions. And I'd say that I think the good news is that every country now at this point acknowledges that climate change is real, it's human caused, it's a threat, and we need to do something about it. There's more that needs to be done from there, but over the past couple of weeks, we've seen Brazil step up with a plan, the U.S. step up, China, and then even India. And while India's plan, wasn't necessarily very ambitious, the fact that they even came forward with a plan was seen as progress, right? And so, I think the question is, what will come out of Paris? I think at this point, folks expect some kind of agreement, but it's not clear how ambitious the agreement would be. And I think there's thorny issues. Some of the thorny issues relate actually to the Green Climate Fund. Hillary Clinton at COP15, which was Copenhagen in 2009, was able to create this pledge of $100 billion annually by 2020 for developing countries to mitigate, to kind of leapfrog beyond fossil fuels, and to adapt to the extreme weather events that they're dealing with. And that $100 billion, so if the hard targets were emissions before, I think what we're seeing now is that the hard part now is around the dollars and how much countries are going to put forward. I think the president attempted to put $3 billion towards the fund Republican Congress is going to fight that. The French have put $5.6 billion forward. So I think if hard targets around emissions were the thorny issues in the past, I think now the money is probably going to be the harder issue. So I think on that note, I will just say, just keep track of it. You know, you can follow Christiana Figueres, the head of the UNFCCC, on Twitter, and there's so many different ways to just be a part of the conversation. And don't forget about Thanksgiving. So that's important too. And I think I'll wrap it up there and take questions.
Much to Heidi for an eye-opening or even eye-widening talk. And for those of you that were here last week for the lecture about exoplanets, I think you had a marvelous transition of thinking about the search for potentially habitable exoplanets, planets orbiting stars other than the sun, to thinking about how to best sustain and prolong the habitability of our own planet. So thinking globally really is thinking locally in that case. So we will open the floor to questions now. So if you have a question, please come to one of the mics in either of the aisles, and Dr. Cullen will take your questions.
We kept it nice and cold so no one can fall asleep.
Should we go first here? Or?
Yeah, sure.
I can't help but remarking there's an event going on across town at the same time, actually, with Christine Lagarde and Lawrence Summers, and they're discussing capitalism and morality. And when I knew of this event and coming to it, and I heard that advertised, my optimism about the affects that we could have on the changing state of climate went down. Because I feel, and I'm just thinking out loud first, I feel that there's this juggernaut of global capitalism that is the enemy, if you will. And I am an American and am a participant in the whole scheme, but it convinces me that the changes have to take place on such a base individual level. So my question is, the power of science, which is great, not just in terms of the wonderful predictions that you've made as scientists, but the power of science seems to be so sort of cloistered amid our larger social fabric. And I wonder, from your perspective, what sort of things are scientists in the climate realm, but also just across the board who are part of all of the predictions, what are they doing to expand themselves so they are working more closely with economists and with psychologists and social scientists so that we get to the behavioral level? Because considering the demographic here, and I'm part of that, you know, we're all concerned about our retirement, and will I have enough to be comfortable, and is life going to be hard for me? And it's so, there's these big, huge issues for us. So yeah. I'm wondering about the exposure that you are getting.
Yes, let's start with the easy question first, right? You know, I think that at the academic level, you know, sort of at the institutional level, I think we're really recognizing that this is one of those thorny problems that can't be solved in a stove-piped manner. And Chris Field, I don't know if Chris is here. He's got a plane that he was coming in on tonight. But you know, a place like the Carnegie Institution out at Stanford is attempting to do this, and you know, and it's not just Stanford. I mean, there's other places that are really trying to connect these different disciplines, because it's really going to have to be this solving across multiple equations, if you will, to come up with an optimal solution. But I think you're right. You know, it's going to have to be felt at kind of all levels. There has to be a shift. You know, in the discussion about India, you know, India for the longest time really didn't want to be part of this negotiation, because obviously economic growth was the paradigm. That was the most important thing for India, and that's fair, right? I think the carbon footprint of the average American is now about 17 tons, and the average carbon footprint of someone in India is about 2. And so it's this recognition that kind of everyone wants to have this kind of lifestyle, and how are we going to do that? So I do think that having this multidisciplinary approach is a step in the right direction. The question is, can we do it fast enough to get it all done in time? And thanks for coming to this talk instead of theirs.
My question is this. It seems to me the real elephant in the room is the fantastic spike in human population on this planet as a species of animal. Do climate scientists actually consider maybe ways we could try to reduce human population, or at least not encourage its growth? And do they try to do any kind of quantitative work to see what the relationship is? It seems that I never see that in the graphs.
Yeah. It's one of those topics that I do think is a really hard one to talk about. And I remember when I was at Columbia, there was actually a book that was written by Joel Cohn, who was at Rockefeller. And Joel wrote a book called How Many People Can the Earth Support? And it really gets into some of these questions about habitability and the carrying capacity of the planet. And I think at this point, in the RCP projections and things like that, population growth is a part of it. And I guess, what's the projection now? 10 billion by 2050, roughly. So that has to be factored into the way we manage resources. But that book may be one that would be of interest.
Hi. I spent a couple of years recently with NOAA and EPA going around the country working on case studies of extreme events. We couldn't call it climate change. It had to be extreme events was the term we used, and studying them and effects, especially on water and wastewater treatment plants. That happened to be what we were looking at, but we also brought in as many people as we could who were affected to talk about what happened and what the plans were for the future. What we found, and my question is about, all right, very discouraging. We invited energy people, nobody showed up, really. And what was so discouraging is that there was an incredible, first of all, the scientific illiteracy I find in my work is astonishing, absolutely flummoxing and astonishing. But beyond that, there's also a real distrust of scientists. How many times I heard people say, oh, scientists, those graphics, you can Photoshop the graphics. You can make up your own results. And this is prevalent. It's really a challenge, and it's going to be a slog. My question is, I see that you have collaborated with journalists and scientists, and that's fine, but you're all up there at the very top of Maslow's hierarchy in the White Tower, I'm thinking, what other collaborations, this is something I've been really wrestling with, would really make a fundamental difference in those 42 states that are suing because they don't believe in this stuff. This stuff can only be solved, as the previous questioner said, at the local level. I mean, we have all these companies maybe coming in, but really this is stuff we deal with at the state and local level.
Yeah.
And even, So I'm thinking the health industry, this would affect people. Can you collaborate with teachers so that the science can get done in schools and kids are graduating understanding, what science is and what they can trust? College kids, young kids today really care deeply about this, but they're apathy. I don't see them as apathetic. I see them as being left out of the conversation and feeling like there is no answer or solution. Like, we created it, and
All right.
they're gonna buy themselves a tiki hut somewhere. So, where else can you collaborate so that all of those issues can be addressed?
Yeah, I think you've also pinpointed this fact that we can't do this in isolation. And I mentioned at the top, one of the things that we've been doing is working with local TV meteorologists. And I think for me, just because I was part of the Weather Channel and recognized how important local TV meteorologists were in their communities and seen as scientists in their communities. So that's one of the reasons why we've reached out and have been working really closely to provide local TV meteorologists with, and I should say, localized content, because you're right, it has to be local, it has to be close to home. And I think that's just, I'll give you that one example, but I'll say, don't despair, because because it's really easy to, right? Because it's just like, wow, this is so big and so hard, and everyone else is at the capitalism talk right now, right? So I think it's just to say, look, there are groups that are trying to do all of those things, and you know, we're in DC. You know, there's an NGO community headquartered down here, and there are people who are now working night and day on the Clean Power Plan to do all that needs to be done to win those battles. And I think that there's also great work being done at the college level. A woman by the name of Wendy Abrams just helped coordinate an event called No Tomorrow, where they worked together with all of these universities. And it's like, when you actually talk, and you're right, not every college kid cares about the issue, but the ones that do, I think, really, really do, and I think we all need to find each other.
And also, please drill down a little bit more. I am shocked, no, I'm not shocked, at how many kids graduate from high school not understanding the first thing about science, even in vaunted counties like Fairfax and Montgomery, I'm sorry to say.
Yeah. We need science.
Just a question, no speeches. I was challenged by a friend. I have a friend that asked me a question which I couldn't answer. He does not think this is a real problem. He said, since the Industrial Revolution started, how much carbon, how many tons of carbon, fossil carbon, was basically taken out of the ground and put in the air? And I have no idea where to find that. The totals, some 1850 to today, X trillion tons of carbon, fossil carbon, I don't know. Mm-hmm. Tell me where to find it.
Email me. I can send you the graphic, because the calculation has been done, and it's 40-something gigatons or something. I'm sure somebody in the audience who knows the calculation, but we've done the calculation, and that answer can be provided. But you have to tell him that if we give him the graphic, he has to change his mind. Right? Can you do that?
Yeah, I'll try.
You said in the talk once
Right. Right, and that needs to be translated into tons of CO2, I think, or tons of carbon, depending on which one he wants.
How much carbon?
Yeah.
Great question.
Yeah. I think it's something like 40-something gigatons.
Cullen, I wonder if you can comment.
400. Mike, how much?
Closer to the
500 or 600. Yeah, not 40, 400. Yeah, of carbon. Okay, so, and it has basically been going up every year, so we can get that graphic.
I wonder if you can comment on the overall impact of methane emissions relative to CO2, particularly with regard to all these frac sites that are out there.
Yeah. There's been some great reporting done on it, so there's a part of me that wants to just refer you to our website. Groups like EDF have been working on finding out how much has been going up. Actually, the Years of Living Dangerously, the show that I worked on, we did an episode on methane. And so basically, because methane is an even more intense greenhouse gas than CO2, it's got a shorter lifetime. So it's one of these things where if the sites are leaking, then natural gas is not as clean as we think it is. But I would say follow up with me. I can send you to some really nice analyses that have been done. But the EDF website will also have, it was a PNAS paper by Steve Pacala from Princeton that essentially did the calculation.
Okay, thank you.
I'm sure we could keep Dr. Cullen here all night asking questions, but I think we just have time for one more question from each aisle.
Two quick things. One, you mentioned Years of Living Dangerously. Are you involved in the new season of that?
Yeah.
And can you comment on that briefly? And then two, you mentioned all the satellite data. And I've been reading about the fact that a lot of our satellites that do this kind of stuff are nearing their end of life and not being replaced.
Yes.
And that's not getting a lot of attention. Can you comment on that as well?
Yeah, I wrote an op-ed for the New York Times about it, I guess, a year or two ago. Needless to say, I love satellite data, and I think environmental infrastructure is critical, and yeah, that the lack of investment in infrastructure is a big problem. And I think there was an Academy panel that looked into it. But we do need to talk about it more. But I will say I did try. But it is really important. And the Years team is back, and we're working on the new series. It's going to be on Nat Geo this year, so the guys decided to shift from Showtime, which was subscription, to Nat Geo, which is just available in a lot more households. And I think that the goal with the next season is to focus more on the solution so that we don't all feel really depressed about this issue. And in terms of the folks that we've got for correspondence this year, it's always kind of fun to see which celebrities they end up getting. So David Letterman is going to do an episode. If you ever watch Modern Family, Ty Burrell is going to do an episode. Jack Black is going to do an episode. So it's for some reason, a lot of comedians want to be part of this. I'm not really sure why, but we could use them. So yeah, it's going to be coming back, but October of 2016 is when it's going to premiere.
This isn't a question, but I want to get rid of some of the depression in the audience.
Thank you.
I have been contributing and following the Rocky Mountain Institute for a long time with Emory Lovins.
Yeah.
That institute, with its large team of engineers, has come up with a master plan which involves energy efficiency, which involves a change in building automobiles with low carbon fiber, so much lighter, and a huge host of changing the electrical grid and so forth. They published a book, Reinventing Fire. You can go on their line, Rocky Mountain Institute. They believe we could get rid of all fossil fuels, and following the plan, incorporating everything in that book, which is a huge book, that all fossil fuels could be eliminated by 2050.
Yep. They do really good stuff.
Well, since that wasn't a question, in the interest of fairness, we'll allow one more.
I was wondering if you could talk a bit about the hiatus. Specifically, how do you communicate this cause of warming, not just in terms of convincing people that temperatures will continue to rise, but restoring some of the trust in the science?
Yeah. So the question was about the hiatus. So I think there's two things that need to be said, and I actually had to testify before a Senate panel, I think last summer, and this issue came up. And I think the short answer is that there has been some very nice analysis showing that, first of all, roughly 93% of the heat is going into the ocean. And I always want to put that slide in, and I never have enough time. But the oceans are so important, and we don't talk about them enough, and I'm guilty of that too. So a tremendous amount of the heat was shown to be going into the deep ocean. So Kevin Trenberth and others did that analysis. And so basically, the first answer is there was a pause. It's not, a hiatus. It's like even when there's variability, you would expect in a natural system there to be kind of, a flat point before it goes back up again. So it's not, and it's just in the atmosphere that we're seeing it in the atmosphere. But all of these other variables continue to show increasing warmth. So the Arctic is continuing to show significant ice melt. The upper level of the oceans are continuing to warm. The terrestrial biosphere is showing a signature. So if you only pick this one variable, and that is the atmospheric temperature, it leveled off briefly. It was shown that some of the additional heat was going into the deep ocean, and so that was just a very nice analysis that was done. And so really it's just to say that global warming has not stopped at all. So it's just wrong. It's just flat out wrong. And I think I'm getting to the point where I'm old enough now where some people just make stuff up, and it's just wrong, and you have to tell them. I was always well, really, I was always nice about it and tried to give them the best, but no, some people just lie, and it's not true. And so I think you can just say that.
That's great. Thank you again. And before we thank Dr. Cullen one more time, I want to encourage you to join us all on November 12th when Dr. Bob Hazen of our Geophysical Laboratory will talk about the origins of life on Earth. And since scientific literacy has come up more than once this evening, I would encourage you, if you're not on our newsletter mailing list, to sign up in the lobby. Our next issue is going to be a special issue about scientific education, so please read it. That's something we're very involved with here at Carnegie, especially with the Carnegie Academy for Science Education. So let's thank Dr. Cullen again for a fantastic talk.